Let's predict the outcome. With hydrogen bromide and propene, which carbon gets bromine? If you chose the interior carbon, nice. You spotted the rule. Let's unpack why. In this video, you'll learn how electrophilic addition to alkenes works. You'll draw the two-step mechanism, read the energy diagram and spot the rate-limiting step, and apply it to hydrogen bromide addition and acid-catalyzed hydration. Let's start with the model. The pi bond acts as an electron source, donating to hydrogen to make a positively charged carbon that is sp2 and planar. Then the nucleophile adds. Markovnikov placement happens because the first step prefers the more substituted carbocation. As we go, keep an eye on the energy ribbon below. It will glow at each barrier so you can match arrows to energy changes. We'll label the transition states as they appear. Let's start the mechanism. Pi electrons form a carbon-hydrogen bond while bromide leaves. That gives a tertiary positively charged carbon, sp2 and planar. On the diagram, that's the tallest peak. Transition state 1, the rate-limiting step. However, protonation isn't random. It follows the path that makes the more stable carbocation. Tertiary over secondary over primary. That's why the product is Markovnikov. So far, we learned that electrons move from the pi bond, the carbocation is planar, and carbocation stability guides where hydrogen adds. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Next, once the carbocation forms, the nucleophile strikes. With hydrogen bromide, the bromide ion adds. With acid-catalyzed hydration, water adds and then loses a proton. This second step is fast, a smaller bump on the ribbon. Let's put it together. Adding hydrogen bromide across 2-methylpropene gives tert-butyl bromide. Protonation forms the tertiary carbocation, then bromide ion finishes the addition. Let's look at what happens when the nucleophile swaps. In acid-catalyzed hydration, hydronium ion protonates first, then water attacks, and a quick deprotonation yields the alcohol. Same backbone, different partner. A quick caution, carbocation rearrangements, like a 1,2 hydride shift, can form a more stable carbocation before capture. And the anti-Markovnikov addition of hydrogen bromide needs radical peroxide conditions. A different pathway than today's polar mechanism. Let's practice the flow. Pi bond to hydrogen, bond electrons leave with the halide, nucleophile attacks. And if water was the nucleophile, deprotonation reveals the alcohol. Remember, step 1 is usually the rate-limiting hill. To summarize everything, the pi bond donates to hydrogen to give a planar, positively charged carbon, then the nucleophile adds. The first step sets regiochemistry and is often the rate-limiting hill. The second is smaller. The same template explains hydrogen bromide addition and acid-catalyzed hydration. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.